Heliophysics is the study of the Sun and its interactions with the Earth and the solar system. The Sun is an incandescent mass of hydrogen, helium, and other elements. While it appears constant from our vantage point on Earth, it actually has a dynamic and variable system of twisting magnetic fields that cause solar events of unimaginable power. The Sun's energy is generated by thermonuclear reactions, creating extreme temperatures deep within the Sun's core. This energy moves slowly outward, taking over 170,000 years to radiate through the layer of the Sun known as the radiative zone. This energy continues to move toward the surface through convection currents of heated and cooled gas in the convection zone. The Sun's rotation further affects the movement within this zone in an interesting way. The portion of the convection zone closest to the Sun's surface rotates faster at the equator and slower at the poles. However, the portion just above the radiative zone rotates slower at the equator and faster near the poles. The layer between the radiative and convection zones are thought to be where solar magnetic fields are formed, and the differences in the rotation of these zones is thought to be the source of the solar dynamo, the physical process which drives the solar cycle of magnetic activity. The variation in rotation speeds within the convection zone twist the magnetic fields, causing them to deform and shear as they weave their way outward toward the visible surface of our Sun, the photosphere. The photosphere is not smooth, but looks as if it is composed of small grains. These are the tops of convection cells that carry heat upward from deep within the Sun. Scattered among these cells are large clusterings of strong magnetic fields that block the upward flow of energy to the surface. This reduced energy causes sunspots, which are relatively cooler regions that appear darker because they radiate less energy into space. The next layer of the Sun's atmosphere is the relatively thin chromosphere, which is sculpted by magnetic field lines restraining the electrically charged solar plasma. Occasionally larger plasma features, called prominences, form and extend far into the very tenuous and hot corona, sometimes ejecting material away from the Sun. The ionized elements within the corona glow in the X-ray and extreme ultraviolet wavelengths. NASA instruments can image the Sun's corona at these higher energies since the photosphere is quite dim in these wavelengths. The outward flowing plasma of the corona is shaped by these magnetic field lines into tapered forms called coronal streamers and extend millions of miles into space. Magnetic fields that cause sunspots are also the catalyst for solar storms such as solar flares and coronal mass ejections, or CMEs. Flares occur when considerable amounts of magnetic field energy are suddenly converted to heat and light. The subsequent blast sends out electrically charged particles into the solar wind. A CME occurs when magnetic forces overcome pressure and gravity in the solar corona. This lifts a huge mass of solar material from the corona and creates a shock wave that accelerates some of the solar wind's particles to extremely high energies and speeds. This in turn generates radiation in the form of energetic particles. The rates at which flares and CMEs occur are related to the 11-year sunspot cycle. Over the cycle, the number of sunspots increase and decrease, and the magnetic polarity of the Sun changes. At the maximum, several flares and CMEs occur every day. At the minimum, when there are almost no sunspots, flares and CMEs might occur only once or twice per week. Understanding the Sun's natural variations is key to ongoing climate studies. NASA missions continue to collect data about the Sun's activity and variability to better understand the extent to which solar activity is influencing the present-day climate.